Okay, so welcome again to another video for numerical method. And for this video, since we're done with nonlinear algebraic equations, which is finding roots of equation, we will now proceed with linear algebraic equations. So for this video, I will be just explaining to you the whole thing about linear algebraic equations from the analytical method up to solving it into a numerical method. But yeah, I will be just introducing to you at least two numerical methods for this one. So anyway, let's just proceed. So for linear algebraic equation, we have motivation, no? Which is non-computer methods of solving system of equations. So uh, our idea is there are ways to solve linear algebraic equations, no? And by the way, linear algebraic equations, if you try to recall it, it's just solving multiple equations with multiple roots. And there are many ways to solve, no? If you have just two equations with two unknowns, usually you use substitution method, mm, yeah, elimination method. No, there are many ways to solve for two equations. Uh, Ramping that up to three equations, maybe, yeah. We do have to learn matrix, um, operation of matrices, and yeah, how to inverse a matrix. So there are ways so that you could find the multiple unknowns out of multiple equations out of matrix, but you have to learn the operation of matrices. So yeah, I will in the next video I will be showing to you how do we how what are those methods, no? And also, yeah, non-computer methods are useful, no, in solving multiple unknowns, but also there are not applicable for non-computers, which in wherein we need to proceed with those methods that could be applicable for computer methods. Then we have linear algebraic equations and engineering practices. So yeah, I will show you what could be the application for these kind of equations where in such engineering practices or engineering problems could be applied. Okay, so mathematical background. So yeah, we need to know about matrix notations, matrix operating rules, representing linear algebraic equation in matrix form. So because again going back to the basic knowledge of numerical method or the basic engineering mathematical solving method, is that you of course you know how to understand the problem, the engineering problem, and then you need to translate that into a mathematical equation. And one way not to translate is just this one. You know how to translate those equations, those problems into equations, and also learn how to establish that equation. Of course, the rules comes in, so metric rules, notations, and so on and so forth. Then orientation and scope and preview and goals and objectives. Okay, so let's go to engineering practices for linear algebraic equations. Now, uh, for common engineering problems, we usually have systems, no? Systems such as for letter A, this is a lump variable system that involves couple finite components. So, As you can see in the figure, we have an input as your feed, and it goes part to two ways, no? But anyway, you have to understand the what comes in and what comes out. Yeah. Uh, More of which all of the theories that you learn from the other subjects will be applied here so that you could establish the equation. For the next figure, this is a distributed variable system that involves continuum. So different figure or diagram from the figure A, but figure B shows a one path only, no? But in any way, in establishing equation, maybe it would be very different for letter A. Letter A would be much obvious, but for letter B, there might be some factors that you need to consider before that you will establish that equation. So, in anyhow, all of your learnings on theories that you grasp from your other subjects should be equipped, no? Should be applied now before establishing those equations. So, matrix notation. So, I think I will be just yeah, be fast with this one because I think it is already been taught to you by the other or your previous studies, but this is a matrix, no? Usually you have an array of, yeah, you have an array of a columns and a row, no? You have values with columns and you have values with rows, and usually, yeah, the notation for matrix is that for every value position in that way there is a notation. Say for example that is highlighted with white in the figure, which is yeah, the A23, or A the data of the column row, the column 3 and the row 2. And yeah, you write the it's like a positioning system, no? You write first the position of the row, then the column. So it should be A23. It means that it is in row 2 in column 3. Okay? And yeah, there are many types of matrices, no, but I will be just mentioning what we could see in the slide. So special types of square matrices. So yeah, the famous one would be the square matrix, no, wherein you have an equal value of rows and equal value of columns, no. So symmetric matrix. So for example, here I think I should also use a laser, no, so that you could see where I am reading. So yeah, so this is a symmetric matrix or a square matrix. So you could also be using 2 by 2, 4 by 4, as long as there are equal numbers of rows and equal numbers of columns here. So the number of columns is equal to the number of rows. Okay. The next one, which is a diagonal matrix. So it means that all values or all elements in the inside the matrix are in the diagonal uh, portion or position, no? And the other values are equal to 0. So like this one, uh, you only have values for the diagonal yeah, portion. So we have a 1 1, 2 2, 3 3, and 4 4. So all of which and the other values like a1 2, a2 1 are zeros. The next one is the identity matrix. So this one is a diagonal matrix. So same with the previous matrix, but instead you have random numbers for your elements of your main diagonal. Here we only have one value, which is 1. So yeah, this is what we call a identity matrix, no? Then if, yeah, the idea here, if you multiply it with an ordinary matrix, it will be just equal to what is your multiplying. Say for example, for this one, and you are multiplying an identity matrix of also a 3 by 3, then the product of it, it's just equivalent to this one, 5 1 2 1 3 7 2 7 8. So if you don't know how to operate, no, or to do multiplications, additions, subtractions, and divisions for matrices, I suppose that you need to look back or study these things, no, before proceeding with this video, because you will not understand what I'm talking about if you don't have background for matrices. So anyway, I will just be proceeding, no. Yeah, so the next one, which is an upper triangular matrix. So yeah, this one, it has all the values with the main diagonal, and also with the uh upper portions of the matrix, and the lower values are zeros. So if you can see it in this slide, no, the blank space are equal to zeros, while the other has a value. And opposite to it would be called as lower triangular matrix, and where all elements above the main diagonals are zero and the other have the values. Okay, and proceed. Binary matrix. So it has a value for the main diagonal, and yeah, next to the main diagonal would have also a value, but the next one would be equal to zero, say for example for this one. So the diagonal next to the main diagonal has also the values. Okay, and it also have a special name, no, which could be also termed as a tri-diagonal matrix. Okay, so scope and preview. So yeah, so we're here with the linear algebraic equations. I already talked to you the motivation, the background, and the orientation, Gauss elimination. Yeah. So I will be just introducing to you what is it, but I will not show you how to operate it because it's part of the analytical method for finding the multiple roots and multiple equations. Also with the LU decomposition and matrix inversion. Same with the spatial matrices and the Gauss-Seidel. Case studies will be showing to you for the ME applications. What I will be showing you application for solving multiple roots and multiple equations are Jacobi method. Yeah. Yeah. Gauss-Seidel also. So Gauss-Seidel is part of the numerical method there. Okay. So Gauss elimination. So let's say for the equations of 9.1, we have multiple equations with multiple unknowns. Say that you have infinite, yeah, the multiple the unknowns are infinitely established. No, you have we're just saying it could be possible that you have 5 equations, 6 equations, as long as it is equal, no? Let's say uh 2 equations with 3 unknowns, that could not be a possible yeah. There are ways, but it could be a trial and error. But for this slides, for this topic, all of the equations should be limited to equal numbers of unknowns with equal numbers of equations. So let's just say if there are 3 unknowns, there should be 3 equations. So yeah. Then yeah, the graphical method for finding the multiple roots with multiple equations, it's just simply this. So you have to graph those equations, and to where that equation would intersect. Now, where at what point would that intersect? That is the value of your yeah, root. So the value of the root of these two equations is 4, no? And you have 3 also. Yeah. So yeah, x2 is for the vertical and x1 is for the horizontal. So yeah, so you can solve this through substitution elimination method for lesser equations wherein you only have two equations. Yeah, it could also be you could also easily visualize the two equations. But these are linear equations, I suppose. What if you have um parabolic, hyperbolic, cubic equations, or much complicated equations such as trigonometric functions, uh, hyperbolic trigonometric functions, exponential, logarithmic, so on and so forth. So yeah. So let's talk about determinants and Cramer's rule. So the determinant can be illustrated for a set of three equations. So let's just say that you have uh, a matrix A, which is the coefficient matrix. It has equal numbers of equations, equal numbers, the values are getting from the equation, so that let's say you are given with a problem and you have three equations, and let's say you are translating that equation to a matrix and you have the matrix A, and the B yeah, coming also from that equation would be the constant values. Okay, so let's proceed. So the determinant D of this system is formed by the coefficients of the equation as in, so you have uh yeah, the determinant of the matrix A, no? If you don't know the determinants, again, you should step back and uh go again with what are the matrices, the operation of matrices, how to get to the determinants of each matrix, no? Might be a 1 by 1, a 2 by 2, a 3 by 3. So I'll be just proceeding with this one. So once you get the determinant, so yeah, although the determinant and the coefficient matrix are composed of the same elements, so they are completely different mathematical concepts. So that is why they are distinguished visually by using brackets to enclose the matrix and straight lines to enclose the determinant in contrast to a matrix. So the determinant is a single number, for example, the value of the second order. So there is, yeah, let's say we have a matrix D, and to calculate the determinant, it's just crisscrossing, no? Finish up. So let me have a pen here. So okay, like this. So A11 times A22 minus A12 times A21. So that is the value of your matrix. So for third order cases, so a single numerical value, determinant can be computed as. So this is solving determinants through uh um yeah, with a single numerical value, no? Ano siya? So A11 kani siya, then okay, isa pa siya. Like this. So kung unsay wala na trace akong lines here would be multiplied. So that's why this is A11 then multiplied by the determinants of the cofactor, mga the 2 by 2 are what we call as the minors. So that is A22 times 83 minus A32 times A23. So yeah, simplifying mo na siya makuha ang determinants. Then you could also use basket method, no? So you could search that as well. It's the same way you also get the same value of the determinants. Okay, so for Cramer's rule, this rule states that each unknown in a system of linear algebraic equations may be expressed as a fraction of two determinants with denominator d. So, yeah. And with the numerator obtains from the determinant by replacing the column coefficients of the unknown in questions by the constants of b1, b2, to bn, no, so on and so forth. For example, x1 would be computed as, so this time for this part, so sa column 1 would be replaced by a constant, no, and then you have new sets of matrix here since you're replacing the column 1 with the constant, no, the b1, the b2, and the b3, and you divided it by the determinants, and you can compute, no, the the X one. Okay, so let's talk about elimination of unknowns. So elimination of unknowns by combining equations is an algebraic approach that can be illustrated by the sets of two equations. Let's say yeah, you have two unknowns here, which is x1 and the x2, and you have this equation 9.6 and 9.7. And for, yeah, establishing or solving the value of your x1 here by elimination of unknowns is just constructing it. Let me get my pen here. Okay. So, yeah, where are we? So yeah. So in solving these two equations, the 9.6 and 9.7, so translating this first into a matrix form, it would be like A11, A21, A12, then A22. Then the X matrix, which is X1, the X2, equals to the V or the constant matrix, which is B1 and the B2. So by solving again the x1, so replacing the first column, so you have a fraction here, fraction line here. So first column with the constant matrix. So that would be B1 and B2. Then copy the remaining values, which is A1 and A2. 2. Then dividing it with the original matrix, which is A11, A21, and A12, then A22. Then to have a specific value, finding the determinants of each matrix of the numerator and denominator. So denominator, yeah, determinants, and you get each of these values. For x2, yeah, instead of the column 1, you will be replacing the column 2. So with b1 and b2, then the same process goes. So then you get x1 and x2 for this method. So what are the pitfalls of elimination method? So whereas there are many systems of equation that can be solved with naive Gauss elimination, there are some pitfalls that must be explored before writing a general computer program to implement the method. All throughout the following materials relate directly to the naive Gauss elimination. So the information is relevant for other elimination techniques as well. So methods such as division by zeros, round off, and ill conditioned systems. So yeah, there are weaknesses for this method. So the Gauss-Jordan. So the Gauss-Jordan method is the variation of the Gauss elimination. So the major difference is that when an unknown is eliminated in the Gauss-Jordan method, it is eliminated from all other equations rather than just subsequent ones. So in addition, all rows are normalized by dividing them by their pivot elements. Thus, this elimination step results in an identity matrix rather than a triangular matrix. So consequently, so it is not necessary to employ back substitution to obtain the solution. So the method is best illustrated by an example. Now to further elaborate this, I will be just giving to you the whole chapter for the linear algebra equation so that you could self-study what is being taught in this slide, So this somewhat is a shortcut, no, of all the methods for solving linear algebraic equations. So if you want to know for the method for analytical way, so there is an explanation of the given material. Yeah. And we will proceed with LU decomposition and matrix inversion. So for which LU decomposition, I will be just explain how you will get this the rules of this one. For matrix inversion, yeah, it could be a hard way for tinamban or you're writing it on paper, but there is an easy way to apply this in Excel because uh operating matrix in Excel is easier, no, thanks to the new functions uh yeah, embedded on the Excel, no. So you could actually find the roots, no, using the matrix inverse. So yeah, let's talk about the overview of the LU decomposition. So yeah, just as was this case with the Gauss elimination method, the LU decomposition requires pivoting to avoid division by zero. So this is much an improvement for Gauss elimination method. Uh, yeah. Then, however, to simplify the following description, we will defer the issue of pivoting until after the fundamental approach is elaborated. In addition, the following explanation is limited to a set of three simultaneous equations, so the result can be directly extended to n-dimensional systems. So again, just what I've said, when you have equations, you have, and instead of having matrix A and the matrix of the unknowns and the matrix of the constant, so yan transpose ang matrix of the constants to the left hand side so that he get this equation for this. So suppose that for 10.2 could be expressed as in the upper triangular system. So let's just say, yeah, your matrix A, you will what do you call this one? You will try to separate the equation, the matrix for A. So let's just say you have all the values, no. So for this one, U managigamit. So you have U11, U12, U13, U21, U22, U23, U31, U32, then U33. So the first that you have to do is that make an upper triangular system. So you just copy uh, all the values in the upper portions. So the U11, the U22, the U33, then the U12, the U23, then the U13. Then remain as 0 for the rest. So this will be called as your upper matrix, no? Upper ni siya. So that's why it is being used as it is being termed as LU because the term for LU is U for the upper and L for the lower. So which will be explained for the lower. I will be explaining to you, no, for the lower, no, portion. So yeah. So you will be decomposing mo itong terms of decomposition. So you will be decomposing the original matrix. So you have the upper triangular matrix, which we called as U, no? and you have, and for lower you have here lower diagonal matrix, but instead of copying the main diagonal, no, the original values for main diagonal, you will be just setting those values with equal to 1. So copy the other values for the lower values, then for the main diagonal it should be 1. Then yeah, so what could be the so how could we solve for the roots of equation using the two matrices that we get? So before that, no, since you have equations for lower and upper, so one way to just elements, so the original matrix equation kani, di ba, ato mato siyang i-decompose with two matrix. So when you reconfirm it, just to check if you still on track, the two matrix, if you multiply those two matrices, the lower and the upper, it should be equal to the original matrix, no? So one way to confirm it. So let's proceed. Yeah, so that's what explained here, no, kanina portion. So let's proceed. So if this equation holds, it follows from the rules of for the matrixification. So equals gid sila dapat, no? And yeah, the lower times the determinants should be equal to the uh yeah, to the constant matrix, no? So a two-step strategy. So wala ko yung figures for obtaining solution can be based on the equations 10.4 and 10.7. So for LU decomposition step, so A is factored or decompose. So monotono i-decompose nato ang original matrix into two, which is the lower and the upper. Then the substitution step, no, for the next next step for the LU decomposition. So L and U are used to determine the solution of X for the right hand side, B. So this step is consisting of two steps. So first equation 10.8 kani. So when you get the matrix D, nagkuha na siya, is just finding the B matrix and multiplied with the inverse of the lower matrix. So that you can get your D. So yeah. Then the result is substituted into the equation 10.4. So ang 10.4, so mo ni siya. Kani siya. So once makuha ni mo siya, uh, you will try to get the value of X now by multiplying your value of your what you get from the D, then multiplied by the U of the inverse. Because you are just deriving your matrices, and you are dividing uh, the D matrix all over the U matrix, and there is no division in matrix, but you could do multiplication matrix. So but yeah, there is an inverse matrix. So what is the appropriate to do is multiplying the D matrix that you solve from the lower portion, then multiply it with the inverse of the upper matrix. Then after that you get the value of the x root. So mo na siyang LU decomposition. So mo din ni ang figure 10.1. So this just show how you will solve for LU decomposition. So again, for a recap, so for the original matrix, no, A, you will decompose that into two matrix. So we have an upper triangular matrix that you will have the values of your main diagonal, and for lower diagonal matrix, the main diagonal is equal to 1 and the rest will be copied. So yeah, and first, so the lower diagonal triangular matrix will be multiplied. You will find first the inverse of it, and you will multiply it with the constant matrix or the B matrix, so that you have the value of the matrix D. So usually the so di siya square matrix. No, this would be, yeah, a linear matrix, which is, this is not a symmetric matrix. So that value will be proceeding with the operations for the upper triangular matrix, wherein the D matrix, the one that you get from the lower operation, will be multiplied with the inverse of the upper matrix. So you need to find the inverse matrix of the upper, then multiply with the matrix D, then you will have to get now with the X, no? So ang mga unknowns makuha na tayo. So yeah, there are two sections that we could see here. So the first, the one that we operate for the lower triangular matrix are the forward, no, process, and the one that we operate with the upper process is the upper triangular matrix is the backward process. And this operation is what we call the substitution, because you are just making substitutions for each matrices. But yeah, first and foremost, this is the whole stuffs for the LU decomposition. So how about for matrix inverse? So it's so awkward, no, kay nag-mention tawag inverse for the LU decomposition. So what is inverse di? So basically, the notation for inverse has a exponent of -1. So however, there are many ways, no, to solve for the inverse matrix. No, you could find a video for that, or you could read it in the books. But to simplify, when you multiply it with the original matrix, so multiplying it with its inverse, so like this one, so the original matrix is being multiplied with its inverse, the product or the result will be an identity matrix. So recall, an identity matrix is a matrix that has a main diagonal of equivalent to 1, and the other portions will be equal to 0. So more of it is a unity matrix, so equal to 1. Okay? Okay, let's just proceed here. So let's talk about special matrices and Gauss-Seidel. So special matrices, yeah. So in figure 11.1, parameters used to quantify the dimension of the banded system, we have PW and horizontal, yeah, HPW designated as, yeah, the bandwidth and the half bandwidth. No? Then we have tri-diagonal systems. So yeah. So yeah. Maybe for linear algebraic equations, you will not encounter tri-diagonal systems, but maybe in solving partial differential equations, you will end up with tridiagonal systems, not tridiagonal matrix. So yeah. And anyway, the idea here in just solving the unknown will be just the same. No? You could use yeah, the one that we mentioned, the matrix inverse method, the LU decomposition, and the numerical methods such as Gauss-Seidel and Jacobi. Then show, I don't know how to say this, so sorry, so kung wala siya say it properly. So Cholesky decomposition. So for Cholesky, I'm not really quite a fan of this one, but yeah, the resulting triangle factors are transposed of each other. So for 11.2 na equation, so it can be multiplied out and set equal to each other. So the result can be expressed simply by recurrence relations for the kth row. So for its value, we have an equivalent, yeah, equation to find the value of L sub EI, and also for L sub KK, which is the for 11.3 and 11.4. So so much for that. Let's go ahead for the Gauss-Seidel. So I think the Gauss-Seidel is the one I will be focusing with solving linear algebraic equations, because the idea in solving here is very much the same with simple fixed point iteration sa katong roots and final equation, which you could, yeah, you could solve easily. So the first thing is uh yeah, again, no, you have this type of situation. You have matrix A and matrix X and the matrix of the constants, which is termed as the matrix B. So suppose that you have a tree of three. You have three unknowns with three equations. So yeah, instead of you could translate it into matrix, but instead of translating it to matrix, all of those three equations will be yeah, will be derived in such a way that um the the left hand side will be just the x1, so for the first root, and the second equation will for the second root, and the third equations for the third root. So you will be deriving those equations instead of translating it to matrix. You will be deriving it such a way that you will be creating your own formula. So same idea for the simple fixed point. So to consider that also, that your x1, your x2, and your x3 should be contained with variables with the other variables. So say for example for x1, for deriving, you have contains for x2 and x3. So yeah. Yeah. So but maybe for case to case basis, yeah, pwede pod walang x2 na naara po ng x3. So depende no kung unsay kihatag na equation. So yeah, for three unknowns and for three equations, so of course you have three uh, new equations that you'll be using. So you have three governing equations, you have three derived equations, and that derived equations will be, yeah, you will be transforming it into an iteration equation. So those iteration equations will be used in iterating your solutions until you get the values of the roots. No? So convergence criterion for Gauss-Seidel method. So let's say that yeah, you already have the equations. You already established the derive and the iteration equation. So let's just say you start with the first iterations, then you get the x1, the x2, no? Then yeah. So this figure di is just, yeah, we have Gauss-Seidel and we have Jacobi. So just a quick step back. So Jacobi is the first method that is being used before, and then they try to improve the convergence of the method until they end up with Gauss-Seidel. So we have here uh, the different, no, the different placement of values for Gauss-Seidel and for Jacobi. So for letter A, which is the Gauss-Seidel, and for letter B is the Jacobi. So yeah, let's explain first the Gauss-Seidel. Say that you are having your first iteration here, and all of your starting values, let's say for x1, x2, and x3 are zeros, zeros, and zeros. So when you try to solve for the x1, so you substitute the values of x2 and x3 here, which is 0, until you get the value for x1. And proceeding with the next equation, let's say you are finding with the x2. So instead of substituting the value of 0 as your first, yeah, as your initial values for x1, you will use the what you solve in the first equation. No? Since you're finding x1, you will update it in your second equation. Then since we haven't solved the x3, so you will use the initial values, which is 0. And for x3, for the third equation, you'll be updating with the value of x1 here. Wala siya na arrow. And for your x2 here. So, inana siya. So, you are just trying to update the uh the substitution of values, so that you will have uh you until you get the value of the roots. Now let's go for Bino, which is the Jacobi iterative method. So yeah, again, let's say you have initial values for x1 and x2, which is 0, 0, 0. So you have to employ these values for the first iterations. Now you are not updating the values. So for x1, you will employ the values of the initial values for x2 and x3. And for x2, again, you will be using the initial values. So we will not update the values. For x3, yeah, again, using x1 and x3, which is zeros. And then you update those values in the second iteration. So that's the difference between the two. So based on the convergence of these two, it seems that since the Gauss-Seidel is an updated one, we should expect that there is a higher convergence rate for Gauss-Seidel than the Jacobi. But anyway, in this part, in yeah, for this, since we are studying for solving linear algebraic equations, we will try to solve. Uh, we will try to apply these, no, we'll try to apply the Gauss-Seidel and also with the Jacobi. Then we could see it for ourselves, so the difference between the two, and that's all. So yeah, so for the next video we will be showing you how we could, yeah, solve for uh linear algebraic equations using Gauss-Seidel and the Jacobi. No? So thank you for listening, and see you for the next for the video.